Good. Okay, yeah, so hello everybody. Yeah, I'm indeed Bas Nijholt. So I am gonna talk about adaptive, which I think will be a little bit of an easier topic than the previous topics, probably even easier than the introduction topic. So it's about this package called adaptive, but before we dive into what the package exactly does, I'll sketch out the problem that lots of us have, and many of us might not even realize that it is a problem, but you're certainly doing it. So in our research, we often construct some type of mathematical model. We implement that in our Python code, and then we explore some different parameter spaces. I already saw Anton do that in his lecture and some other people as well. And what we often do is you sweep a homogeneous space because simply it's the easiest thing to do. That doesn't take any brain power. So let's look at some simple code. Like we have this very complicated model. It's complicated because that's the name. And then this model, what we're doing is like we're sleeping a random amount of time because the functions that we're calculating are very slow and hard. And then it returns a number. And this function is actually just a line, and then with a peak centered around this offset. Now, okay, then so if we want to know how does this function look like in a certain domain, what we can do is like we do the sweep. We have a linear sweep with n points. Then we calculate the model and then we plot it. So let's see how it looks like for 30 points. Well, there we see. Okay, I told you that it's a peak, but in general, we're sampling like black box functions and we don't really know, but like, okay, at least 30 is not enough because we don't really see a peak. So let's try 50, also not enough. And this is something that typically it now takes like a few milliseconds to show us, but sometimes this happens overnight on the cluster. And then you realize, oh, not enough resolution. Okay, so 100, we found a peak. That's great. So I guess 100 is enough. Just to be sure that we're not missing anything, 200 points. Okay, now we have 200 points and you kind of say like, oh, he's talking about the peak all the time. I guess the peak's important. Why are you not sampling the peak with more points? So now we have only like 6, 7 points in the peak. So I'm saying like, yeah, we could do this better. Like we're wasting a lot of resources on this boring region with a straight line. And then the answer to this, or the solution, I think, is a package called Adaptive. And Adaptive is it's an open source Python package. You can just download it on GitHub. It's a library that makes adaptive and parallel evaluation of functions in low dimensions easy. And it's easy because you only need to supply the function itself and the bounds in between which you want to run or learn about the function. And then everything is automatically parallelized and you can see like your data live or appear live in the notebook as the calculation is in progress. And this project kind of started during my PhD, where I needed to speed up like very large scale simulations of Majorana devices that were run on the cluster. And hopefully this helped. Or thankfully this helped. So you can just install it by going like pip install adaptive. Okay, so let's look at how we calculate this complicated model function that I showed in the beginning adaptively. So we just import adaptive and then activate like the notebook integration for adaptive. So then the way it works is like in adaptive, we have a few concepts. I'll go over in more detail what they mean exactly later. But we can create a learner object, and this is like an oracle, or it's a container for the function and the bounds and the data that we have about the function. So in the beginning, that's nothing. So we construct this learner by just passing the function, the bounds, that's it. And now we want to run this learner, like tell it, okay, evaluate the function at all the cool points. But we also need to tell it when to stop. So we tell it there's a certain goal that needs to be met. So go on until a certain goal has been met. So for the linear space, we said, okay, we want to do it for n points. So we can do something similar. There's a certain interface that we use in adaptive. And what you need to do is you make a function that takes this learner object and then returns true or false. Am I done or not? So we can do this with the number of points, but we can also say, okay, until the loss is below a certain number, and whatever this loss means is what you choose it to mean. But by default, it is for this learner, it's a measure of like what's the distance between the two nearest points. Yeah. You can fully customize this, but by default, it's something that should give you sensible results for most functions. So now we have constructed this learner. We have a goal. Let's say we take this loss goal. Then we construct something called a runner. You pass this learner to the runner, and you give the goal, and then we say, okay, give us some nice information and plot the function. So we do this. Now we see we get some information about the function running. Oh, it's going quite fast. Here you can see that this thing was appearing live. Let's do it one more time because it was too fast. Like you see, like at first it didn't find the peak, and then it found the peak. It starts to. Ooh, this is a bad example. Let's pretend like I have too many cores. And task. Okay, the loss was my goal was too simple for the thing to convert. But okay, so now I can see once it finds some interesting region, it keeps sampling there. So now you see, like with only 50 points or so, we already did a much better job than in the homogeneous case. So, and then you might have also noticed, like when this calculation was going, the kernel wasn't blocked. And what that means is usually if you do a calculation in Python, you can't do anything until you get some result or until the function is done. But in this case, here the function is like calculated on the background. So you're still free to manipulate anything in the notebook. So while this calculation was in progress, we could already look at the data that has been calculated, for example, by looking at learner.data, which is a dictionary of like X values with corresponding Y values. So then we could also decide that we didn't give this thing a goal, that just keep on going forever, and then we can just say cancel when we think it's good enough. So then we can compare like the result to like a homogeneously spaced example. Like here's some code. Ignore that. The only thing we care about is this plot here. So where we have a slider with the number of points. And so on the left side, we have like homogeneous sampling, and on the right side, adaptive sampling. So in the beginning, what it will do, it has an algorithm to select an interval with a certain amount of loss. In the case of here, it's like which points, the adaptive one is which points are furthest apart. And in the homogeneous sampling, it doesn't matter. It just depends on the direction X in X. So like once we add more points, in the beginning, the results are very similar. It will always add a point in between the red dots. And then at this point, it found some point on the peak, and now it will keep focused on the peak. So now, like, yeah, you see, like with 39 points, we go on here, like 50, here it didn't even get anything extra. So that's nice. So now, hopefully, you're convinced that adaptive sampling for these types of problems is better than non-adaptive sampling. So now I want to go a little bit into more detail, like what this learner exactly is and what it can do, or what this runner is. So I already said this learner is just a container for a function and the bounds. And now if we construct this learner, you get back an object. And this object has a few important methods that like are maybe crucial to its understanding. Like one of them is the loss. And this loss is like a quality factor of like how well do the points that I already know at this point describe the underlying function. So if I would just draw a line through all the points, how well do I reconstruct the original function? And this is an estimate of that. So that returns a number, so I can do it. Okay, so for the one that we ran above, I said stop if the loss is less than 0.05. So that's why this is less. Then there's another one called learner.ask. And the ask method is just you ask for new points, like give me new points. So it returns some new points x, and which is a list of points in x, and then also tells you this is how much improvement to the loss each of these points will probably give you. So now what we can do is like we can take one of those points, like let's look at the first one that was suggested, like we asked for 5, we select the first one, then we calculate the value, and then we can tell this value of the suggested point to the learner, and then hopefully this should reduce the loss. And that's hard to see. Yeah, okay, so now the loss is less. So that means like every time that you add more data to the learner, you can expect that the points that it will suggest will become better. So for example, in the beginning, you don't know any data. So then it can do no better than returning you the bounds at which you, of the domain in which you're interested in. So now using these few functions, we can kind of reconstruct a way to like run this learner, to drive it. So what we want to do is something like this code that I wrote down here. So we have the learner, then we say while the learner loss is larger than a certain threshold, ask for some points, and then for these points, calculate the function and tell it, and then go back in the while loop until the loss has reached a certain goal. Now, so that's something that we want to do, but this has some problems. For example, if we just run it like this, we're not using all the resources of our computer. So ideally, we want to parallelize the function execution over all the cores that we have available to us. This could be either on our laptop or on a computational cluster with thousands of cores. And also, if we run it like this, the kernel is blocked. So we would not be able to inspect the data in between or live plot it or something. Now, without telling you how the runner does do it, I'm just saying the runner fixes these problems. So we just pass a learner to the runner and tell it the goal, and then it will be in parallel without blocking the kernel. So that's great. So unfortunately, not all the problems that we're working with are in one dimension. So luckily, we also implemented some other types of learners. Like, so I showed you the 1D learner, which takes a 1D input and can then return a vector or just a single scalar. We also have this for 2D and even for ND. At some moment, you'll run into the curse of dimensionality. So you don't want to sample probably like 4-dimensional spaces like this. But for things that we plot, or can plot, these adaptive sampling methods work rather well, usually. And then we have some other ones like to sample stochastic functions or to do adaptive integration. So just to show you like that we have a uniform interface and like how you would calculate something for a 2D function, I have written down a 2-dimensional function which takes a tuple or something which 2 numbers x, y that we expand here, and then returns this number, and this is a ring in 2D. So now we pass this function like before to the learner object, and we set the bounds. So now when we run this, and we feed this thing to the runner, and we say go on until the goal has been met, we can see like this is the live plot version of that thing. Where here we just see the underlying interpolated values. And here we see like a triangulation where at each point or each vertex of this of each triangle, that's where we calculated one of the points. So we have a denser point grid around the ring than outside of it. So I think I'm reaching my time limits. So there's only a very small part left, but so like adaptive by default chooses new points based on like, for example, distance between the points and tries to minimize that. But sometimes you run into problems where this doesn't work. So then you can customize the logic for where adaptive chooses points. And that I explain here. Basically, you can very easily write a special type of loss, and then you can just supply it to the loss function. And there's many that we already defined ourselves. And then I have made some exercises, which should be rather straightforward. The solutions are right below, so please don't look at them. And then, yeah, if you run into any problems, you can always hit me up on the chat. And thanks for listening.